Hello. Well, first of all, are there any questions until now?
Will you like explain everything in the map dot? Because I've been really trying, and I've just been having to like find YouTube and Stack Overflow. So, like there's a lot of things that I feel we haven't done in class yet. So will everything be covered in the YouTube? I actually feel like YouTube would do better than classes.
Well, definitely for the lab. I think for the lab, I want to do. Actually, for the lab, I definitely want to do YouTube. And I'm going to do videos of how to download the software and how to use it, what happens when you do things, and then I'll start. What I want to do for each targil, I want to start it for you. I want to do like the first 25% or more. Also, for some of the later targeting, I need to really explain what the targil requires, what the lab requires. All right. So anyway, I hope any other questions? No. Okay. So I don't know what you guys have seen, what you haven't seen. I put up a video of.
Yeah. So what's the deadline for the labs? Are there any what are the deadlines for the computer for the homework in the labs?
Well, I mean, I'm not. The only reason to have deadlines at all is so that you don't wait to the end and then not hand it in. So I'm not really, too concerned about deadlines, though I do like to put them so that it gives you an idea. Get your act together and start working. But I'm really not that interested in deadlines. I'm going to use. I think that the director of the course in general, the Rakaz, is going to set dates for all of the students, and I'll probably just leave whatever he does. I can also change for our group, but I think I'll just leave whatever he does. So it should be in the place where you put it in. It's in Hebrew, but you can see it just says 1, 2, 3, 4. Where it is there, I think you'll have a date written there. But they're all open now, so if you've done anything, you can certainly hand it in now. And they'll be just pass fail, or pretty much, or maybe actually I just saw now he said you could give a 50 also, so it can be 0, 50, or 100. Basically, I hope everybody gets 100, which means that their programs work.
You're gonna.
Of course, if you get 1 0 and a bunch of hundreds, it's still going to be a pretty high average.
You're gonna be making a video though on how to install the software properly.
Yes.
Because if we do it wrong the first time, you said it won't work ever or something like that, right?
Yeah, sometimes it doesn't work out. So I'll make a video exactly how to do it. Yes. That's the first thing I'll do, I guess. Yeah. Okay. So as far as the videos, there's already chapter 5. I think at 4 and 5 are up on the Moodle. So let's do 6. And in 6, we'll actually kind of review chapter 4, which is the single cycle. So because we're going to be looking all the time at the single cycle structure. Now, really, if you're lost, you have to go back and go through all the chapters up till now. And you'll have to watch this. You can stay and watch this video now, but you should watch it again afterward because everything is based on what's come before. Okay, I'm going to share my screen. Yeah, here, I'll share this one. Okay, so here is chapter 6, computer architecture, additions to the MIPS chip to support additional commands. The idea here is we are going to take the basic diagram that we've seen and add some more wires to it so that it supports commands that up till now we didn't consider, we didn't think about them. And up to now, actually, they wouldn't have worked. Or we didn't think about them much. For example, a jump command. Actually, I don't know why he didn't start with jump. It would be better to start with jump command. But the jump command, there's no way to do it in the basic design that we've seen. In other words, there aren't the wires there. And other commands too. We've shown you basically a limited diagram, a diagram missing certain lines. And now we're going to try to add stuff to it. And this is going to be important for homework number 3 and 4 because they're both requesting you, I'm talking about homework now in the lecture, they're both requesting you to take the basic diagram and add lines, add hardware so that it can support a new command. So that's what I said over here. Now, when we are going to add something, well, first of all, let's, oh, did I switch the order here? No, this is, I switched the order here. Let me change this slide. Sorry, just a second. Okay, things to consider when enhancing the chip. So that's what we're doing. We're enhancing the chip. So we need four, we're basically gonna have to answer 4 questions every time. Now it's in the homework or now, every time you want to add some hardware to an existing computer, you have to answer these 4 questions. One is, what extra hardware are you adding? We can add any hardware we want as long as we can imagine that it could work with logic gates like AND and OR and NAND. For example, a sign extend unit. We could have we could add a unit that does sign extension. We can add an ALU, but we can add anything, and we don't have to explain how it works internally. We can view it as a black box. For example, in the example that we're going to do, we're going to add over here, well, like for example here, we add a shift left 2. We have something that does shift left 2, but okay. When we do add it, we have to say what the values on the new control lines will be. In other words, if we've added something here, we got a controller, and these are control lines. They control different hardware pieces. If we add another hardware piece, let's say over here, we're gonna have a new line controlling it. We're gonna have to say what value will be on it. Will it be 0 or 1? And when will it be 0? And when will it be 1? Questions? No? Okay. Yeah.
What do we write above that line? We just write what it is.
We'll name, yes, we'll talk about that. We'll name the lines. What will be the values on the new lines for that hardware in all the cycles? If it's multi-cycle, we have to think about what the value of the control line will be for cycles 1, 2, 3, 4, and 5. If it's single cycle, then obviously it's just one cycle, so just one value that'll be on it. And there theoretically could be changes to other control lines. It could be that, and what changes there will be, if any, to the existing control lines. In other words, theoretically, there could be a change to what already was there. Furthermore, 3, what output will be created by the new component in each cycle? So if we add something, we add some hardware over here, I don't know, the Nachum's black box, what is it going to produce? What's output? Obviously, we have to explain. But what is it going to produce on all? If it might sometimes, based on different control lines, different numbers, it might produce different outputs. So therefore, it might produce different outputs on different cycles. If it could have 3 control lines, and theoretically, and then those lines could tell it to do different things on different cycles. So we've got to explain what it does on every cycle. Of course, if we're talking about single cycle, then we don't need to explain what it does in every cycle because it's just one cycle. And the final thing is, what will the values on the new lines be when executing other commands? In other words, let's say we added this hardware to support a certain command, Nachum's command. Now, what will the value on that for Nachum's black box be when we're doing a regular add or a regular subtract or a load word? We have to explain what the lines will be when not in use. In other words, when not being used for the command that we're adding. So this may sound a little bit theoretical. We have to see an example. So here's the example. LUI, there's a command LUI. And LUI does load upper immediate. Now, if I go over here, you see, yeah. If I go over here, I see the LUI command is a command, actually. We didn't think about this command when we looked at the diagram till now, but it is a command, and we have to think about how it would work. What does it do? Actually, I think I talked about it with you guys at length. But if you remember, it takes these 16 bits. This is here. These I's represent the I's for the word immediate. And there's 16 of them because the immediate sits in 16-bit spaces. So if he types, let's say 100, it'll sit somewhere in these I's. So this is the actual encoding. This is how the command will look. The opcode is 001111. The RS is blank, doesn't matter what's in the RS. But the RT will be the 5 bits of the RT will be the register that's written here. And what this does is it takes this immediate value and sticks it into this register. But it doesn't stick it straight into the register. First, it shifts it to the left. And where is that immediate stored? As we said, it's over here. So that's what the I does. It takes a 16-bit value, puts it into the register, into the register after having performed a shift left operation of 16 spaces. So if the number was, let's say, 1 over here, 00001, we're going to shift it left. It's going to become like 60, I don't know, 32,000, 64,000. It's going to become, you know, it's going to become, yeah, I think 64,000. It'll become 1 to the 16th power. So, you know, not 1 to the 16th power, 1 times 2 to the 16th power. So that is what the LUI does. And if we look, let's go, where were we? No. Here. I can't see my tabs because of there. You can see my screen now?
No.
Can anybody see my screen?
No.
No.
What?
No.
No. No.
No. Okay. So I must have done something. Share screen. There. I must have unshared. I must have unshared. Okay. Now you see my screen. Yeah.
Yes.
Okay. So the LUI command, we need to explain what changes must be made to allow the LUI command to work. This is fine. The LUI is an I-type command, obviously, because it's got an immediate value. The command is supposed to move the 16 bits. We said that. The diagram of the single cycle, there's clearly no way to perform this instruction. Well, first of all, that's the way he writes in his book, and it's just obvious there's no way to do it. I mean, there's nothing that does a 16-bit left shift here. There's no hardware that does that. There's a sign extender, but that doesn't do 16-bit shift left. There's an ALU. I could shift something a bunch of times with using the ALU maybe, but then I'd have to use multiple cycles, and we want to do this in one cycle. So there's no way to do it. So therefore, we're going to add hardware. What hardware we're going to add? We're going to make a black box that we're going to call zero extend swap. And what it does is it receives 16 bits, and it puts out 32 bits, which is the same 16 bits shifted left, 16 places, and added zeros in. So if it was 11111 over here, it'll be 11111, and then 000, 16 zeros after. So that's the 32 bits that are going to come out of this thing. And how it works? Well, we know that we could make something like that with logic gates. We don't have to explain how it works. It's a black box. Now, if we look at the diagram that we're going to make, here's what we're going to do. We are going to take this zero extend swap, and we're going to connect up 16 lines from the instruction. And because remember, the instruction has the immediate value in places 0 to 15. We're going to connect that. We're going to connect them with this wire and put them through our new device. It's going to come out 32 bits, and it's going to run along here and go into this multiplexer here, who is going to then decide whether or not to pass it on. If it does decide to pass it on, where is it going to go? It's going to go down this 32-bit line and up into the register file. Well, remember, the LUI is supposed to write to a register, so that's exactly where it should go, to the register file. Now, it should go to this register file, and it should write that data into the right data. Under which file? Under which register in the register file? Well, there's 32. We've got to choose one. Well, the one we chose is the one in the RT. Now, here's the RT, and it's going here. It's also coming to this multiplexer, and this multiplexer, if we select 0 on it, will forward the value straight into the right register selector. And whatever he wrote in RT, which is 16 to 20, will go into the right register. And if he chose, for example, 17, so 17 will be here, and whatever this shift after, whatever we produced after our zero extend swap did its work, will come in and be written to register 16. So we've done it. We have added now, but now I want to compare this diagram to the previous diagram so you can see what we changed. We obviously added this, we added this line. What about this multiplexer? Was it there before or not? Well, notice that there's some lines coming into it aside from our line. There's two lines coming into it. One from the read data and one from the ALU result. Well,
I
let's
think it used to
look
be a 2-to-1 multiplexer, I think.
there. So if you remember well, let's go look at it. There was a multiplexer over here. It was a 1-2.
Or
It was
the
a
one, yeah.
it was exactly the same multiplexer with the read data from the data memory and the ALU result, and it was just two possibilities. And it also went down to here. So we didn't change anything. What did we change? We just expanded this multiplexer. We took it off and threw it away and went to the store and bought another multiplexer with a larger number of entrance ports. Now, when you buy a multiplexer in the store, you can either buy a 2 multiplexer, a 4, an 8, 16, a 32, 64, 128. You can't get a 3 one. We really want a 3 one. We want 0, 1, and 2. We just want 3 entrances. But they don't sell those, so we're going to have to buy a 4 one and just not use one of the entrance lines. So we buy the 4 one, we stick it in here, we add our new line from here. Remember this 15? We added our machine right over here. So let's go look at the picture again, to the new picture. You see, we've added our piece. It comes in, and now we've got, well, he wrote 0, 1, and 2. But let's look at it in fine, but notice he wrote multiplexer 4-to-1. It's a 4-to-1 multiplexer. It takes 4 entrances and puts 1 output. Let's look at this in finer detail. We can see that over here. Here's the multiplexer. Notice that it's 0, 1, 2, 3, and with 0, 1, 2, and the 3 has no connector because we don't need it, but we had to buy it. So now we have the ALU result, the read data, those were the existing lines, and the new line is our new zero extend swap, our 32 bits that we wanted to put in. And again, coming out as this. And the control lines, what about the control lines? Well, if we look before, there was one control line here called memory to register, because it decides whether the memory result should go to the register or not. If it's 1, then it takes the memory result and sends it to the register. If it's 0, it doesn't. It takes the ALU result and puts it to the register. So it's called the memory to register because it decides whether the memory, if it's true, then the memory will go. So those two lines are going to be in this picture. Sorry, not those two lines. The control line here, which is either a 1 or a 0, is in this picture where it's here, memory to register. It's the existing line. We're going to call it S0. We're going to plug it into the S0 port of the multiplexer. Because a 4 multiplexer is going to always have 2-bit controller. So the other bit is going to be a new line. We were going to call it the LUI line. And it's going to come in. And basically what's going to happen is if it's a 1 and this is a 0, then we're going to send a 1, 0 is obviously 2, the value 2, and that's going to send this value through. Remember, this is like a filter. It chooses one of these values to pass through. And which one? If we put 1, 0 here, there's 1 on our new line and 0 on our old line, then we're going to get 2, and we're going to choose this one, and we're going to send our 32-bit extended result. Now, if you notice over here, that's exactly what I have. If the new line, S1, is 0, 0, then, is 0, then if the old line is 0, then it's ALU result, and that's what we had before. And if the S0 is 1, then read data to memory is what's sent through. That's what we had before. But if the new line is a 1 and the old line is a 0, then the zero extend swap gets sent through. That's just a table form. And in your homework, you should write some table like this to explain exactly what happens. And furthermore, we have to write a table like this, which is showing the control lines, all the control lines for the new instruction. We have a new instruction, LUI. We've got to say what's on every single one of these lines. So let's take a look at it. Notice that everything is 0, or XX means don't care. Why 2X's? Because this is 2 lines, actually. This is 2 bits. And this is don't care. And the only ones are the register write and the LUI. Those are the only ones that we have here. Everything else is either 0 or don't care. Well, don't care could mean 0 also. So let's look at the diagram and see why we have those results, why we have those control lines. Well, first of all, question.
Yeah, what exactly does the new piece do?
What exactly does what do?
The new piece, the zero extend swap.
What does it do? It takes a 16-bit result and turns it into a 32-bit result by shifting it left 16 places. I can draw it. Is that not clear?
Yeah, no, it's good.
It's good. Okay. So let's look at our first of all, here's our new line. Notice we called it LUI. It goes up, down, and it hits in right there. And that's our new control line. Now the controller is going to know to put a 1 on this line because he's getting the opcode here. 26 to 31 is the opcode. He's getting the opcode right in here. And that's telling him this is a LUI command, LUI command. So he says, oh, it's LUI. I'm going to put a 1 on this line. And that's great. Now he's going to put a 1 on this line. He's going to put a 0 on this line. Well, that's what I've written here, 0. What else is he going to put a 1 on? Well, the only other thing he's going to put a 1 on is the write register, which is this. Now, what that 1 means is that this register file is open for writing. It's open for business. In other words, this data that's going to come through here to the write port, it could, if this register file is locked, it's not enabled, then even though I wrote this data here, it won't get written. It'll just sit there at the port and won't get in. But I have to open up the door. And that's what this 1 says. It says true, allow writing to occur. So that's what we want because we need to write to the register that he gave us. So that's the other 1. Everything else is 0. Why? Well, for example, we talked about these 2 ones, this being 0 and this being 1. What about these 2? So the memory write is a 0. It has to be a 0 because if I write a 0 on memory write, then that's essentially locking the memory. Because this is not a command to store something in memory. This is not supposed to write to memory. So I need to lock the memory because otherwise some data, some random data that the ALU will create, because the ALU is going to run, it's there. It's like a part of the engine that's running. So when I go through this cycle, the ALU is not like turned off. He's going to produce some result. And that result is going to go to the write address. And if I don't put a 0 here, it's going to get written to some place in memory that this line produced. Some random place in memory, not random, but some place that I don't know what it is, will get written to. And I don't want that to happen because that would be a side effect. That would be some other action that happens when I'm doing an LUI. So I must put a 0 on this line to lock this piece up. This piece I have to put a 1 on to open it up. Now everything else is also a 0, and we can explain why each one is a 0. For example, the branch. The branch has to be 0 because on the LUI command, I don't want to also do a branch. And I want to do, what does that mean I don't want to also do a branch? I want the PC to go up by 4, like it normally does. Well, the PC came in here, went up by 4. It goes through here to this multiplexer, and as long as I choose 0 on this, it's going to go all the way back into the PC, and the PC will now be incremented by 4. But I better darn sure choose 0 here. If I choose 1, then I'm going to get some other result, and it's not going to be incremented by 4. It's going to be some other value. Well, how do I control to make sure I choose 0? Well, this has to be a 0. Well, this is an AND. An AND means that as long as one of them is 0, as long as one of the entrances is 0, then for sure the result will be 0. So if I put on branch 0 over here, then for sure the output will be 0. Then he'll for sure choose this, and that will mean he'll choose the PC plus 4 to go to PC. So I need to have that branch be 0. If I had it be 1, then it's possible that the other input that this ALU produced could be also a 1, and then I could get some crazy result going in here. So I need the branch to be 1.
The output from the ALU, it's a 0. Isn't that always 0?
The ALU is 0 when the result is non-0. When the result is 0, the ALU 0 is 1. So most of the time, the ALU 0 will be 0. But sometimes it'll be 1 if the 2 numbers that came in here and here are identical, and it did a subtract. Right? If I subtract 7 from 7, then 0 is true. It is 0. Because again, everything is working all the time. Just because I'm doing an LUI doesn't mean the ALU is not functioning. The other lines also, well, the other major important line is this line, the register destination 0. That's very important. Where does that go? That goes to this multiplexer. And this multiplexer, basically, it says the RT comes along here and it says, should I let the RT go through or should I let the RD go through to the right register? Well, if you remember in the LUI command, let's look at the, oh, do I have it still? Yeah, in the LUI command, it's the second register. The RS is here and the RT is where I want to put it, or I want to put this value, the RT DAFCA. And we could wonder, why didn't they use the RS? Why did they skip the RS and use the RT? They could have used either. There's 2 registers, we only need 1 of them. Why did it use DAFCA, the second one? So we can understand why. Because the RT already has a line going to this multiplexer. That's an existing multiplexer. And that's an existing line already going, and it has the ability to be moved into the right register selector. So when our data came over here onto this data and we wanted to know where to write it, we wanted to write it to the RT. Well, the RT already had a connection to here because of this line and this 0. And then, so if we had chosen the RS for our LUI command, then we would have had to add another line here to this multiplexer and make this multiplexer a 4-to-1 multiplexer and add another control line. Much simpler to just use the RT, which already has a way of getting there. But we have to put on this control line a 0, as you see a 0 here, so that we select that result to go to the right register. So that's it. We have explained this table. We've explained 4. In all other instructions, the LUI line will be 0. Notice our new line will be 0 for every other instruction. That way it won't have any effect on anything else.
No, any existing command would write to RS at this point, right? It would have been a made-up command.
Well, I don't hear so. Any existing?
Anything that exists right now that writes to a register, that any command that exists would never write to RS. Only something that is made up that you would say,
Yes.
we want to make this would only write to RS.
Yes. Given this architecture, there is no way to ever write to the RS. It is impossible. You can only write to the RT or to the RD. RD and the RT both come into this multiplexer, and both of them could potentially be the right register, the register to which I want to write. RS is not possible. But when I'm adding stuff, I can add anything I want, you know? So we could theoretically add it. I'm just saying it would be dumb.
Yeah, okay.
That's all.
I'm wondering, how does the multiplexer, that 2 multiplexer work, but with between RT and RD? I can't really figure out which wire is the one that chooses between them.
This control line, the bottom here.
Okay.
This control line, it goes up, and here it's register destination. A little bit small.
Yeah.
Register destination. So it's on the bottom here is a control line. By the way, I updated this chapter 6 and the Moodle, and it's now got these pictures, got all the pictures here. Fine. So we basically finished. Here is just some, I just explained now what, remember, one of the things we had to do, remember, we had to answer these 4 questions. We had to explain what does it do in all 3 stages. So in all 5 stages. So if it's multi-cycle, we really have 5 cycles, and we really have to explain it. Here, we also have to explain it, but we call them stages because they're really just time periods within the single cycle, like at the beginning of the cycle, the middle of the cycle, the end of the cycle. So in the beginning of the cycle, the first 2 stages is identical to all instructions. So our instructions will be no different. It'll just do whatever they normally did, which, if you remember, was PC plus 4, calculate the branch address, a few other things. But what's interesting is stage 3, where we finally know what the command is, and we say, oh, 0 extend swap. We're gonna run. It'll work now. Finally, the data will, by stage 3, have reached this guy, and he'll have produced a 32-bit result. I mean, by the way, this guy is going to work now in every single operation. Every time I do any command now, a load word or anything, this guy's going to still get his data, still produce his result, and it's going to still hit this multiplexer. It's just that we're never going to choose that line. And so it'll sit there and go to waste. Back to here.
Does that affect performance in any way, or because it's, I guess, electrical?
I would say it heats. It doesn't. It heats up the chip a little bit.
Oh, okay.
Because there's one more thing working, so the engine gets a little bit hotter. I got a new laptop a month ago, and one thing I like it. It's not a particularly good one, but one thing I'd like about it is that it has fans. It has like a good fanning system, so it doesn't get too hot, because the heat actually makes it work less efficiently. I sometimes in my car, if I put the Waze on, I put the phone right over the air conditioning exit, and I keep the phone nice and cold, and then my battery doesn't die. The heat is the enemy of efficiency for electrical circuits.
So this was actually the answer for a single cycle, right? What would be different for a multi-cycle in the answer?
Well, first of all, the diagram would look different. I mean, well, it wouldn't look too much different for this particular thing. Might not be any different. Remember, the diagram is different. It has more control lines. It has no add over here. It's a little bit of a different diagram for multi-cycle. We could do it the same exact way. I mean, in the sense that we would still create this black box, and we would still have to add a control line to some multiplexer, but it might be a different multiplexer. It might actually make a 4. This might already be a 4 multiplexer, and we might have to use an 8 multiplexer. You see, because it's still only one more line of control lines. Because remember that, right? One more 3 bits is already up to 8. So it might change. It might look a little different. That's all. But as far as this diagram, as far as this part, it'll still be the same. This slide will look the same. In other words, this will be stage 1, stage 2, and stage 3, and not stage 1, cycle 1, cycle 2, cycle 3, and cycle 4. So this page will look the same. So let's talk about this again. 0 extend swap. It'll produce a 32-bit result, which is the immediate. And these two vertical lines mean appended to. Appended at the end of it will be, on the right side of it will be 16 zeros. That's what this thing will do. The control line LUI1, well, that's what we said, that's the S1. And the memory 2 register, which is the S0, those two will be 1 and 0, which is the value 2. That'll cause that multiplexer that we added to select the result, and it'll send it on its way, and it'll go down the line, but it won't get written to the register. In other words, it'll go down this line, but only in stage 4 will the register file finally get the electricity. And he will say the selected data will pass from the multiplexer output to the right data lines of the RF. Right? It'll go down those lines to the RF, and now the control line register destination 0, we talked about that, causes the multiplexer to pass the RT instead of the RD to the right register of the RF. And he's already got the data from the right data line, and now he's got which register, and the register right being 1, as we talked about, will cause that LUI data to be actually written to the register. I was just explaining what happens in detail for each stage. So we've explained, because I said it in words, but you need to say it in writing. So in your homework, for example, there's not enough to just write these control lines. You've got to write, okay, here I wrote what the control lines do. Here I wrote what the control lines will be for this command and for other commands. And here I show the diagram. And here I say how it's actually going to work. Another example. Before I go there, any questions on that? Okay, let me do this other example. This one's even easier, actually. Supporting the jump command. The jump command is actually the simplest thing to do, because all we're doing is changing the PC to some other value. Instead of the PC being PC plus 4, it's going to be whatever the jump tells us to do. Remember, if we go over here and we look at the jump command, the jump command is jump target. It means PC equals new PC. Just take this 26-bit value and do some massaging to it, change it a little bit, and it's going to go into the PC, not into any register, into the PC. I mean, the PC is a register, but not into any register that we select. So we just write 0, 0, 0, 0, 1, 0. So it's 2. It's what did I say? Control. It's opcode 2, and the rest, the other 26 bits, is where to jump to. Now remember, if we talked about it, well, I'll explain it in my slides. What does it actually do? It takes that target address that's here. It adds 2 zeros to the right. That already turns it from 26 to 28 bits. Still needs 4 more bits to be a full-fledged address. So it gets another 4 bits from the top of the PC, from the most significant bits of the PC. And this plus here actually means append. I really should have written 2 lines, but whatever. It means append. So append those 4 bits to the target address and add 2 zeros. And now I've got a 32-bit result. That's what we want to do. The basic single cycle diagram we have seen does not support the jump instruction. Sometimes I have shown a fuller diagram that does support the jump instruction, but let us relate now to the basic diagram. In other words, the basic diagram would not have the jump in it, even though right here there's no jump in it. There's no jump. Actually, I have previously shown you a diagram with the jump logic over here. But there's no jump in this command. There's no way to do a jump. There's nothing that, how do I know there's nothing that does a jump? Because in order to do a jump, I need a line coming out of this instruction with from 0 to 25, 26 bits going somewhere. I don't have that. I don't see that. I don't see any line of 26 bits. I see 6 bits going here, 5 bits here. I see 5 bits going here. I see 15 bits going here, 15 bits going here. Let me say 16 and 16 going here. I don't see any 26 bits going anywhere. So for sure, in this diagram, there's no way to do a jump command. I don't have access to all those 16 bits in one place, on one wire, on one set of wires. Remember, this is not one wire here. This is 6 wires. We just draw one line because it's easier. So there is no way to do it. In order to do it, we're going to need something that takes the target address and shifts it left 2 spaces. That effectively puts the 2 zeros here. So we're going to need a shift left 2. That's the name of the device. Like there's a multiplexer, there's a device called a shift left 2, which is a shift left 2 spaces. Shift left by 2. That gives us the 2 zeros over here. And then we'll need to splice in the 4 leftmost bits of the PC. In other words, well, I'll show you in the diagram. Just a second. First of all, here we go. Here is our shift left 2. We called it B, just for clarity in the diagram. Shift left 2B. He takes 26 bits, and he produces 28 bits because if he did that shift left. But I need 32 bits, so what I do is I splice in 4 lines. And what do I mean by splice in? Maybe that's not the right word, but what I mean is think of it, for example, like a major highway. Let's say you have a 8-lane highway, and it's driving along, and then merges in, well, not merges, connect in 4 more lanes. So now you have 8 lines, and then 4 lanes. So now you have 12 lanes of cars, a very wide highway now. In other words, they're not merging. They're just, those lanes joined in, and now the highway got wider. That's what these 4 are doing. We have 28 lane highway going this way, and then these 4 lines, they don't join in anywhere. There's no circle there. See, if they would actually connect, there would be a dot there, a black circle. But there's no black circle there. They just join in and continue on their merry way, running next to the 32. So now this one line represents all 32 lanes of the highway. Just look at the diagram here. You see when I connect something, I put a dot here. Even if the, let's see if I can have an error at the ending one. Yeah, here, look, this 32 goes over to here and there's a circle there. It's not an arrow, it's a circle because it's connected. It's not, right, it's connected here. That's what they circle. That's the difference between an arrowhead and a circle. It means whether it's just reaching that place and continuing on, or it's actually connecting to some other lines. So that's what we're going to add.
Wait, why are we merging in the PC plus 4? Shouldn't we just merge in the PC itself?
No, because that's the requirements. That's what we said over here. The address is the target, which is 26 bits plus 2 zeros, plus prepended to it 32 bits. In other words, bits number 31, 30, 29, 28 are the of our new thing are this identical to bits number 31, 30, 29, and 28 of the PC. So we need to go
And not the PC plus 4.
PC, I'm sorry, PC plus 4. Yeah, I just call it PC because it gets confusing if I write PC plus 4 and then plus.
Oh.
You're right. I mean PC plus 4. Well, that's exactly what we did here. We took
So
the
it's
PC.
of the future PC, meaning of
Exactly.
the next.
Well, let's look at the diagram and you'll see exactly what we do. Here, let me make it bigger.
But that only makes a difference if you're right on the edge, moving into.
Yes,
moving into
it'll only
26.
make a difference if you're right on the edge, as we talked about. You're right. It won't always make a difference. Here, that's much better, right? Is that better?
Right.
Yeah.
Much better.
Yeah. So we have the 32 bits. Now we're gonna look. We put a black circle here. We patched in. We made these wires continue on their merry way this way, but also continue up here and go into our shift left 2. So we've got, and which bits do we have? Which lines? Not all of them, just 0 to 25. I mean, just 26 of them, of the 32. And they go in here and they become 28 bits. And then they continue on their merry way. But in the meantime, remember the PC, we not only did it go in here and fetch our address, fetch our command, our instruction, it also goes up to here to this add so that it can be added to 4, so that it can be incremented to the next place. And before it gets any further, we jump in and grab it. But we don't grab it all. Remember, this is a 32-bit result, 32 plus 4, and it's going to be still 32 bits. But we jump in and splice in 4 lines and steal, we sort of like eavesdrop. We grab the 20 bits, 28, 29, 30, 31, and we put them over here. Here he drew a circle. I would disagree, and it should be an arrowhead. Because it's not actually splicing in, it's adding to. Anyway, the 28 comes in, these 4 come in, and out comes 32. So we've created our address. We've taken the instruction, we've added 2 zeros to the right, and now we've spliced in 4 more lines over here. And they come all the way down to this multiplexer. This is a new multiplexer that we're gonna add. And as long as we choose 1, then this result will continue going and go all the way to the PC. Now, why do we put a multiplexer here? Because we don't always want to do a jump. Not every command jumps. If it's an add command, it's not supposed to jump. If it's a LUI command, it's not supposed to jump. Only a jump command is supposed to jump. So we're going to have a controller here, which we're going to call jump. And that is a new control line. And we're going to add it here. And he's going to go all the way to this last multiplexer. And if he's 1, that means that it's a jump command. That means he's going to choose this result. And if he chose that result, it's going to go all the way to the PC, and we're done.
So
We're
even
totally
even if you're not doing a jump command, that's still happening in the background.
Even if we're not doing, if we don't put a 1 on this line, if we put on this jump line, if we put a 0 on this line, and he chooses whatever comes through here, it's still going to do its job. The electricity will still go down this line and still go through this and still come through and still create that result, and it'll run into a brick wall over here.
Okay, is that considered inefficient, or it's just electricity?
No, that's necessary. That's computer architecture. That's what you do. You add when you need command. That's why we don't want too many commands in our chip, right? Remember we talked about this in the beginning of the course, RISC, reduced instruction set chipset. Some chipsets are reduced instructions, which is MIPS is a reduced instruction. In other words, the more specialized instructions you have, the more hardware you're going to have, the bigger your chip will be, the hotter it will get, the more expensive it will be to make, and the less efficient it'll be. I mean, on the other hand, you're going to have all these special commands that you can get things done in very quick, one cycle. If you have You know what I mean? You'll have specially made hardware to do stuff. That's why a graphic card is different from a CPU, from the main chip of the computer, because the graphic card has special hardware for doing things related to video, which would be inefficient to have in the CPU all the time. But since the graphic card's only doing that, we're gonna add some special commands there. So again, it's not inefficient, it's necessary. But as we start adding stuff, our chip gets more and more complicated. But that's the nature of reality. It's like saying, is it inefficient to have a automatic, I don't know, automatic, have an air conditioner in your car? Yeah, it's inefficient, but you want to have an air conditioner. You don't want a car without an air conditioner. Is it inefficient to have, all these things add to the engine and make it have to do more stuff. So anyway, yes, it's always doing this. But it doesn't, it's always doing this command. Everything I add, the electricity just now is going there. It's going everywhere. I can't stop it. Anyway, but that's what the multiplexer does. It stops it. It says, don't take that result and put it on. Rather take the normal PC plus 4, let it come through here, let it come through this multiplexer, and over here it comes down here into the place 0. Select 0, and the regular PC plus 4 will get put back into the PC. And that's what I want. Now, what about all these control lines? Well, if it's a jump command, basically you're going to have a lot of don't cares, because I don't care what the ALU does. I don't care if he does add, subtract. I don't care. I don't care which one is selected over here, because I'm not doing any writing. But wait a second. I've got to make sure I don't do any writing. I don't want by accident to write something. So what do I got to do? I got to lock the register file. How do I lock it? The same way we did before. Or last time we locked the memory. Here we're going to lock the register file. So reg write would be 0. A 0 over here means do not write anything to the register file. Furthermore, we're going to lock the memory write. And notice you forgot an R there. I didn't make this diagram. Memory write will also be locked. And that's over here because we don't want to accidentally write to the memory. So basically, we don't want to write to the memory. We don't want to write to this because we're not doing anything. We're just jumping. Everything else is don't care. And that makes sense. Now let's see. Here he just wrote that all out. Don't care, don't care, don't care, don't care. Don't write to memory. Don't write to RF. 1, choose 1 to jump to address. Choose 0 for all other instructions. That's these lines. Okay, so we've explained that. And this is the last slide. And good. We'll stop here. Basically, I just explained what happens in each stage. Identical to all instructions. 26 bits of the target address. Right? This is how we calculated it. I just explained the first 2 are everything that we've always done. That, making the PC go to 4 plus 4, making the branch address, etc. But in 3, we're going to finish our command. Notice there's no 4 or 5 because we're going to finish it immediately. It's a very simple command. It's just do all these splicings of lines together, produce this thing, and pass it through the multiplexer. We're going to label it E. That's what I labeled it in this diagram. It's got an E over here. We label the multiplexer. We label all the pieces that we want to, that are for clarity's sake. We're going to say multiplex. If we just say the multiplexer on the right, it sounds kind of dumb. Although I sometimes do that. We want to say multiplexer E. So that's what we do here. We're going to add this. The address is passed to the top right multiplexer, the new one. We compute. Wait a second. I can't see. The control line is jump equals 1. Causes that multiplexer to choose this address and pass it on to the PC. To the PC register. Remember the PC, that's a register there. So that the address for the next instruction will be changed to the jump address. And why is that PC a register? Because we want it to persist. We need a register anytime we need persistence. We need that the data should remain between cycles. And even if this is a multi-cycle, we need the PC to still be there for the next cycle, which is the next command. Because then we're going to read a new command. So we need a register here. Nothing else is a register here except what's in the register file. Whereas in the multi-cycle, we had many registers. Here we only need 1, but we definitely need this 1 to preserve the result that we got for the next instruction. All right, that's it. You have a couple of minutes for questions if you have any questions.
Yeah, I was wondering on that, just on the diagram, how the PC gets updated normally, like without the jump command. I didn't really see where the add 4 goes back to the PC.
Okay, wait a second. Unfortunately, I just stopped my share screen. No. Why don't I have my there, share screen. Share screen. Share. View. So right up here, the PC comes here, add 4. This is a 4. This is like a hardwired 4 over here. This means that the value 100 is sitting here. And that goes into the add, and I do whatever was the PC plus 4, and it comes through here, and I can ignore this stuff because these are all going to be multiplexed out. But it comes up here, through this line, to this multiplexer. And on this multiplexer, I'm going to choose 0. And he's going to come to this multiplexer. And on this multiplexer, I'm also going to choose 0, not 1, because it's not a jump. And that means that the PC plus 4 is going to go on this line. Does that answer the question?
Yeah, I get it. All right, thanks.
Sure. Any other questions? All right, so yeah, go ahead.
2 questions. Sorry, I know my audio was kind of messed up. But my first question is for the jump command. This is just for your standard jump command, but for there are a couple other different jump commands. Am I wrong? And how does a chip, do those jump commands?
So yes, there's only one other jump command. That's the jump and link. What you mean is there's also like jump register. The jump register is, I mean, it's a jump command, but it's actually not a jump type. It's jump register is an I type, or maybe it's an R type. I don't remember. But yeah, jump register. How does it work? So I think that might be your homework, or yeah, you would have to figure it out. I'm not going to go through it all now, but yes, you're 100% right. What I've showed you is just how the unconditional jump works, not how a branch did. So those are a kind of jumps. The only other jumps are jump and link, which basically just stores the PC plus 4 in a register RA. Well, that's pretty simple. We'd have another register over here, which is the RA register. We'd just have a line, coming through with a multiplexer and another control line telling it yes or no to store the PC in that. That we jump and link. That's the only other J type. And as far as jump register, well, that's a little more complicated because then I'm not calculating the address based on the instruction. I'm calculating it based on the register that I was given and what its value is. So I'll have to do a read from the register file, get the result out, and send it somehow up and to the PC. Right? I'll have to read something from the register file, and that's a jump register. So that'll be a longer command. But obviously, there's a whole book of commands. I'm not going to go through them all. I went through 2. But clearly, you're right. This is not explaining every jump command.
All right, I have another question.
Yeah.
So for the jump command, from the the other control lines are, except for the writing control lines, are all set to don't care. I was wondering if they're set to don't care, wouldn't they take some of the processing power as opposed to if they're all set to 0?
Okay, I'll fix it. No, it's not going to take any processing power. It's certainly not taking any. When we say don't care, that's really a logical answer. In reality, physically, we'd have to build it one way or the other. In other words, the control, you see what I'm saying? remember we had a little diagram of how the controller looks, and it has ands and a whole bunch of ands and ors and nots. We'd have to build it that when it got command jump, which is 0001, 001111, when it got that command to produce a particular thing on this line. It just means that from an architectural standpoint, when we're telling engineer, we don't care what ands he uses, we don't care whether he gets a 1 here or a 0 here. But he'll obviously, when he builds that controller, it'll be one way or the other permanently. It's not going to be sometimes 1 and sometimes 0. Don't care is just in our specification. It's like if we're designing a building, and we're saying what kind of metal should the hull of the ship, not a building, let's say a battleship, for engineers of a battleship, we design what thickness and what type of steel, what exact type of steel should be used in the hull of the ship, because we want it to be a certain strength. But when we talk about, let's say, I don't know, the water, the pipe, I don't know, what's a good example? I don't know, the metal table in the dining room, we say stainless steel, and we don't specify which kind of stainless steel the tabletop should be made out of, because it's a don't care. We don't care from an engineering point of view. Whatever the builder chooses to use, it'll be fine. I mean, whatever. I mean, maybe we would specify in that case, but the point is, here we don't care what the engineer actually builds when he builds this controller. Obviously, you can't actually send don't care on a line. You either send a 0 or a 1. Does that clarify something?
Yeah, that's fine. Thank you.
Any other questions? Okay, so send me an email, please, everybody. You can send me to a one-line email to Targilim Danzig, how you want the class to go in the future, video or live. I suspect you prefer live, but let me know. Okay.
I think we'll vote on it and send one, as opposed to like sending 30 separate emails and have to count. We'll just do a vote.
Fine, that's fine with me. As long as you guys arrange it.
Okay, voting booth is open. You're welcome.
Okay.
We have one. Anyway. Thank you very much.
Sure, my pleasure. I'll post this video on YouTube, unless there's objections. If there are objections, speak now.
YouTube is great.
Okay. All right. End meeting.